Look at this visual mapping of a simple lunch order. You need to pick one drink, priced at $1, $2, or $3, and one main dish, costing either $3 or $4. The goal is to spend exactly $5. To figure out how many combinations hit that target, you can easily brute force the answer. You just mentally draw lines between the valid pairs: a $1 drink with a $4 dish, or a $2 drink with a $3 dish. That gives you exactly 2 ways to buy lunch. Now imagine the constraints increase. You have a handful of pennies, nickels, and dimes, and you need to know exactly how many different ways you can combine them to make 23 cents. Try to mentally map that out, and the brute force method collapses. You are suddenly tracking dozens of overlapping combinations: 2 dimes and 3 pennies, or 1 dime and 2 nickels and 3 pennies. Tracking these ratios by hand is slow, and the risk of missing a combination is high. To solve problems with this many overlapping variables, we must stop counting manually. We need a mathematical system that handles the structural heavy lifting automatically. As the complexity of choices scales up, human arithmetic hits a hard limit. We need to shift from simple listing to a system of algebraic organization. A generating function provides mathematical grammar. The variable x is a structural label, a container. The exponent tracks target size. For a $5 lunch, we seek x to the 5th. The coefficient is our counter. A 2 means 2 ways to hit that target. Translating choices uses 2 rules. First, or translates to addition. A $1, $2, or $3 drink becomes a string of terms linked by plus signs. Second, and means multiplication. Choosing a drink and a dish means grouping equations in parentheses and multiplying them together. This grammar maps the messy reality of choice onto the solvable laws of algebra. Pennies form a polynomial where exponents increase by 1. Nickels form a second string, jumping by 5, and dimes jump by 10. Multiplying them finds combinations by automatically adding exponents. The algebra pairs everything. We simply isolate the term with our 23-cent target. The math reveals a coefficient of 9. Because the multiplication process has paired every possible combination of coin values that could sum to our target, we know there are exactly 9 ways to make change. The system adapts to limits. Needing 8 cents using at most 2 nickels and 3 pennies means using short, finite polynomials. When multiplied, they produce a single term for our target, 1x to the 8th. There's only one way to meet those constraints. Generating functions act as an automated accounting system, processing overlapping constraints that would overwhelm manual calculation. A generating function acts as a mathematical zip file, compressing massive amounts of combinatorial data into a single compact expression. One algebraic string can store an infinite sequence of counting answers for every possible variation of a problem simultaneously. This tool allows researchers to calculate dice probabilities in games, route pathways through city grids, and analyze complex data structures in computer science. Algebra provides a highly precise language for organizing reality. It allows a single polynomial to track thousands of distinct physical possibilities at once, making the underlying structure of a problem visible. By translating messy choices into clean equations, generating functions reveal the elegant, predictable patterns hidden within the act of counting.